Module B talks about linear programming. And with this chapter, make sure that you pay attention to what I teach in these videos versus some of what you find in the textbook, because I am not going to test you on everything that you see in the textbook. It's also very important that you look in the section under the module for Module B to make sure that you get the right documents so that you can download Microsoft Solver. So you are going to need Microsoft Solver to do a lot of the problems in your homework and to follow along with this lecture recording. So make sure that you've looked at how to download Microsoft Solver. Make sure that you do that. And when we get to some of our next couple of videos and we walk through some examples together, you will absolutely need that so that you can complete your homework. You can also use Palm for those of you that were able to download that. That can help you to do some of the homework problems there, but you do not need Palm to make it through Module B. So Module B, linear programming, is really, it helps organizations to decide what product mix to make to either maximize profits or minimize costs. So there are lots of things that we can use linear programming for. The reason we use linear programming is because organizations have limited resources. So think about this for a second, and let's just assume that Apple made all of their products in one facility. Now they don't, but let's just, for sake of conversation, assume that they did. In this household, I've got an iPad, an iWatch, and an iPhone. So I have 3 Apple products, okay? The iPad, the Apple Watch, and the iPhone. And let's just say that those 3 products were all made in the same building by Apple. In that building, they've only got so many people. So let's say they've got 10,000 employees. And let's say they have 1,000 printed circuit board assembly machines and other machines that are required to put their various Apple products together. They've also got so much time in the day. They've also got so much that they can use for the utilities. And so there's all these different constraints that they would have to making these 3 different products. So if Apple wanted to determine what's the way that they could maximize profit, given the fact that they had limited constraints, they might determine every day we only want to make so many iPhones versus iPads versus the Apple Watches. And they would be able to say, okay, we're okay if we can't make enough Apple Watches to support demand because we're going to maximize our profit selling as many iPhones as we can. Now, that's just an example. Most businesses have constraints. Apple might not. So maybe they weren't the best example because they're going to use different subcontractors and those subcontractors probably only build one product, but I digress. So we use linear programming to determine what products we want to make to maximize profit, or we can also use linear programming to determine how we can minimize resources to minimize our costs. So some of our learning objectives for Module B are to formulate linear programming models, including an objective function and our constraints. We want to recognize our decision variables, the objective function, and the constraints when we create a linear optimization model. We're going to solve for linear programming, and we're going to use the algebraic method. We're going to use Microsoft Solver to solve for linear optimization models using some spreadsheets. And then we're going to have to interpret those linear programming models. So on your exam, you will not be able to access Microsoft Solver. So what I will do is I will actually complete the solutions for you. I will provide you with an answer report and a sensitivity analysis. I will give you the answers, but you're going to have to be able to interpret the data that I provide, especially given that there will be changes to the sensitivity analysis. Okay, so let's dive in. So with linear programming, we need to know a few fundamental definitions. And the first one is, what is a model? So a model represents the essential features of an object, system, or a problem and looks at the important details of that model. It's a simplified version of reality. These mathematical models help to make things, to calculate out, essentially finding our answer. They're fast, they're cheap, and they're safe because we can look at real data and we can manipulate them as we get new data. So as things change, we can revise the model and it will then revise the output of that model. Optimization models are models that seek to maximize or minimize some objective function while satisfying a set of constraints. Constraints are kind of what I talked about on the introductory slide right there, that, you know, maybe we've only got 10,000 labor hours, or maybe we've got 1,000 different pieces of machines within our facility. So those are constraints. Okay, if you have unlimited resources, then you don't need to do linear programming because you'll just make as much as you possibly can. Product mix doesn't matter, so you wouldn't need to use a linear programming type model because you've got an unlimited capacity. So there has to be some kind of constraint, whether it be machinery, labor, square footage, whatever it may be. You've got to have some constraints. So optimization models are attempting to find out how do we maximize our profit or minimize our costs given those constraints. And so linear programming is a mathematical technique that will help us to determine which products to make, which resources to use, and how to allocate our resources. So the uses of linear programming. Many operations management decisions involve trying to make the most effective use of those resources. Linear programming helps us to solve that. It helps us to maximize something or minimize something. So uses of linear programming could be when we schedule school buses, we want to minimize the total distance traveled. We can allocate police patrol units to high crime areas to minimize response times for 911 calls. So we're going to talk a lot about maximizing profit in the examples that we use, but you can also use linear programming to minimize things as well, whether it be costs or distance or ingredients. So you can use linear programming for minimizing things. You can also use it for maximizing things. So maximizing profit, maximizing revenues, and those are all uses for linear programming. So now we've got some requirements for linear programming. There's 4 key ones that we need to have. The first one is linear programming problems seek to maximize or minimize some quantity, usually profit or cost, expressed as an objective function. We'll go over objective function, our constraints and decision variables and all that in the next couple slides. But we're trying to maximize or minimize some quantity, and that will be our objective function. The presence of restrictions or constraints limit the degree to which we can pursue that objective of maximizing profit or minimizing costs. There must be alternative courses of action to choose from. So my example of can we make the Apple Watch, the iPod, or the iPhone, those are alternative courses of actions. They can choose to make more of one product than another. Those are alternatives. And then the objective and the constraints in linear programming problems must be expressed in terms of linear equations and inequalities. That means that when we've got, our people or our equipment, that if it takes 3 hours to make a part, then 2 parts would take 6 hours. That's a linear type of model. Okay, 3 parts would take 9 hours. So that's linearity and with linear equations and inequalities. The other requirements of linear programming, there must be limited resources. So we've talked about that. You can't have unlimited capacity. Otherwise, you just build everything that you get demand for. You've got to have an explicit objective, that is such as maximizing profit or minimizing cost. You've got to have linearity and divisibility. Again, that goes back to if it takes you 3 hours to complete one part, it's going to take you 6 hours to complete 2, 9 hours to complete 3. That's linearity and divisibility. And then homogeneity means that the equipment and the people are used to build all of the products. So when I said earlier 10,000 laborers who would work in the Apple facility, those laborers are assumed to be able to build the iPhone, the iPod, and the Apple Watch. Otherwise, you would just change the amount of constraints that you have and the resources that you have if they were only dedicated to one product line. But if the machines and the labor cross-pollinate, that's homogeneity. Okay? All right, so linear programming model components. There are 3 key components of linear programming. There's the decision variables, an objective function, and the constraints. Decision variables are the controllable input variable that represent the key decisions that a manager has to make to achieve their objective. That's generally used as x1, x2, x3, and that list can go on of however many decision variables that you have. Decision variables are under your control, okay, and that's that's the input variables, okay. That's essentially the problem we're trying to solve for. Do I make x1, x2, or x3? The objective function is the evaluation criteria, which is generally maximizing profit or minimizing cost. And the objective function coefficients are the constant terms in the objective function, so things that cannot change. Well, they generally do not change. So the profit per unit would be a good example of the objective function coefficients, because the profit isn't going to change as you sell more or less of a product. The profit stays the same. So that's something that is part of the constant terms. Constraints are some limitation or requirement that must be satisfied by the solution. So there's three types of constraints. There's the upper limit, where the amount used is less than or equal to of the resource. There's the lower limits, where the amount used is greater than or equal to the amount of resources. And then there's the equalities, where the amount used is equal to the amount of resources. So again, when we talk about constraints, that's our labor, that's our equipment, that's material. We have constraints with all of those. We can either, we can only use so much, so we're constrained by that resource. And then the solution, there can be any particular combination of decision variables. So there's the feasible solutions, and those are solutions that satisfy all of our constraints, but we're not really focused on feasible solutions. What we want are the optimal solutions. That's any feasible solution that optimizes the objective function. So either maximizing our profit or minimizing our cost, or whatever it is that we're trying to solve for in that objective function. So think about when we did the economic order quantities in the quantity discount models, there was various different feasible solutions, but we're trying to solve for the optimal solution, okay? We want to find what's going to maximize our profit or minimize our costs. So that's the best solution, and that's the optimal solution that we're shooting for. Okay, so before we move on, let's summarize real quick a couple of the key components of linear programming. So I just want to go back and say it again, that our decision variables, an example of that would be how many products should we produce? Our objective function is what product mix will help us to maximize our profit. And an example of constraints would be what are our labor, our equipment, and our material constraints that we've got available to us. So what are our constraints? So for linear programming model components, there's one last thing that needs to be brought up, and that's essentially that the decision variables must be divisible and non-linear, or sorry, non-negative. They have to be linear. Okay, so rewind there a couple seconds. They must be linear, but they cannot be non-negative. So what we mean by non-negative, I'll just use the Apple Watch, the iPod, and the iPhone as an example again. If Apple is working at that facility to try and maximize their profit, and they're determining of those three products which one they want to make, or what mix of those three products they want to make, they cannot get more capacity by building negative something. Okay, they can't build 500 iPhones and 500 iPads and negative 100 of the Apple Watches to get more capacity. It sounds silly to have to say that out loud, but for these models, the lowest you can go is 0. Okay, you cannot go negative, so they will always fall into that top quadrant. The lowest you can go is 0 for something, and that doesn't help you to increase the amount of capacity that you have. You can't go negative to increase your capacity, so the best you can do, or the worst you can do, would be 0 of a product. Okay, couple of the linear programming, mathematical programming conventions. So your objective function, when we write them out and we put this into Excel, or we write out what our objective function is going to be, we're always going to write it as a function of z. So we're either going to maximize z, which is maximizing profit most of the time, or minimizing z, which is generally reducing our costs or reducing the amount of distance traveled or reducing in the ingredients. But essentially maximizing z would be maximizing profit, or minimizing z would be to minimize our costs. Our decision variables must be greater than or equal to 0. You can't have anything negative as a decision variable, like we talked about on that last slide. Our standard notations, and we'll go over this more as we walk through the example in Microsoft Excel, but Z is on your left-hand side, and your decision variables are on your right-hand side of the equation. And then our constraints, they have to be greater than or equal to 0, or they have to be less than or equal to 0, or they can be equal to. But it's important to note the way that we write them out in Microsoft Excel. This is how we say it or type it out in Word and PowerPoint, and just when we're writing something out, this is greater than or equal to. But we can't do that in Excel. So for Excel, this is how it's written out. This is how it's typed out in Microsoft Excel. So these are our constraints. Greater than or equal to is typed out there. Less than or equal to is typed out in this manner. So, formulating and solving the model. How do we structure this problem? Well, the first thing we do is define in words the objective that we're trying to achieve. Okay, what is it that we're trying to achieve? We're trying to maximize profit or minimize costs. Next, we list the decisions that are to be made. So, am I trying to build Apple Watches, iPods, and iPhones? That would be my X1, my X2, and my X3. Write out the objective function. So write out that objective that we discussed. So maximizing profit would be max Z equals something. And then we list the constraining factors that affect these decisions. So what are our constraints that do not allow us to easily maximize our profit if we had unlimited resources? So what are the constraints that are holding us back that we are trying to solve for? So that's how we formulate the model. We think through what it is we're trying to solve. We write out the decisions that we're trying to make. We determine what our objective function is, and then we write out our constraints. There's many ways to solve these models. I'm going to focus primarily on the simplex method in Microsoft Excel and the algebraic method. The book goes over the graphical methods, which are the ISO profit line solution and the 4 corner point methods. It spends 2 or 3 pages on those different methods. And I don't like those methods because to me they are inefficient. You can get right to the chase using the simplex method in Microsoft Excel, or you can do the algebraic method, which the book no longer mentions. So in this revision of the textbook, they take out the algebraic methods and they only talk about the ISO profit line and the 4 corner method. If I was the publisher, I would have done the exact opposite. I would have taken out the inefficient graphical methods that you have to do by hand and guess at, and I would have only showed the algebraic method, because for the graphical methods and the algebraic methods, you can only do that when you've got 2 decision variables. So you might as well calculate it out and go straight to the answer. Figure out what my answer is using the algebraic method. If you've got more than 2 decision variables, then go straight to the simplex method in Microsoft Excel or use Palm. So if you've got 2 decision variables, you can determine the answer using the algebraic method. If you've got 3 or more, then you can't use the algebraic methods. You can't use any of the graphical methods, so go straight to the simplex method. Okay? So that's what we are going to go over in the next couple videos of how do we put this into Microsoft Excel, or how do we solve this algebraically. All right, so let's talk about an example before we walk through together in Microsoft Excel how to do the simplex method. So Glickman Electronics, okay, Glickman Electronics. They are an electronics company in Washington, D.C. that produces 2 products. The Glickman XPod, a portable music player, not to be confused with the iPod, and the Glickman Blueberry, not to be confused with the BlackBerry, an internet-connected color telephone. So yeah, there's no Blueberries and there's no more BlackBerries either. So Glickman makes the XPod and the Blueberry. The production process for each of these products is similar. There's 240 hours of electronic assembly time available, and there's 100 hours of available assembly time available. Okay, so you got 240 hours worth of electronics and 100 hours worth of assembly time available in that facility. Each XPod takes 4 hours of electronic work and 2 hours in the assembly shop. Each Blueberry requires 3 hours in the electronics and 1 hour in the assembly area. Each XPod sold yields a profit of $7, and every Blueberry yields a profit of $5. What is the best combination of XPods and blueberries to reach the maximum profit? So this is a very real-life example, even though Glickman Electronics is made up and these products are made up. They've got two products. They've got a facility that shares resources between the electronic work and the assembly work. Those products take different amount of times to build, and those products make a different profit. So some people have asked me in the past, why wouldn't they just go and only make XPods if they're making $7 profit per unit? Why wouldn't they just not make any blueberries? Well, the blueberries take less capacity or less resources. They are easier to make the blueberries. You can see instead of taking 4 hours, like the XPod does, it only takes 3 hours in electronics and it only takes 1 hour in assembly. That's why some companies make a ton of money on low profit products that are easy to make and they can do high volumes of them. So linear programming takes the guessing out of it, and we can input these constraints, decision variables, and our objective functions into Microsoft Excel, and it'll tell us exactly how many products to make and what our profit will be. So that's what we're going to do with Glickman Electronics. So here's all the data that will be given to you. If you summarize it in a chart, and you just kind of write it out a little differently, it takes you for an XPod, which is your X1. This is something worth pointing out. If I give you this information, and I don't tell you what your X1 is and your X2, always go in order. XPods was provided first, so they're your first decision variable. That's your first X1. Blueberries was the second product listed, so that's your X2. So XPods is X1, blueberries is X2. In the electronic department, it takes 4 hours to produce an XPod and 3 hours to produce a blueberry. You have 240 hours available every week in the electronic area. For assembly, it takes 2 hours per XPod and 1 hour per blueberry, and you have 100 hours available per week. You make $7 worth of profit for every XPod and $5 worth of profit for every blueberry. So the question we're asking ourselves is, what is the best combination of XPods and blueberries to reach our maximum profit? Okay, so before we go on to the next couple slides where we're going to, keep just driving down these what these definitions mean, what's your decision variable? Your decision variables are your XPods and your blueberries. What's your constraints? Your constraints are electronic and the assembly work. What's your objective function? Your objective function is to maximize profit. Okay, so those are our decision variables, our constraints, and our objective functions. So for Glickman Electronics, your decision variables are X1 is your number of XPods to produce. Your X2 is your number of blueberries to produce. Okay, so when we went over those 4 steps, we said, okay, what is it we're trying to solve for? Our step 2 is list out the decisions that are to be made. So the decisions to be made are, do we make our X1 or do we make our X2? Those are our 2 decision variables. There are 2 products. For the objective function, the next step in linear programming is to write down the objective function. So this is our evaluation criteria, either maximizing profit or minimizing cost. So for Glickman Electronics, our profit is $7 per XPod and $5 per blueberry. So our objective function formula is to maximize Z, given our 2 objective function coefficients, which are our constant terms, $7 worth of profit for every XPod that is not 7 multiplied by 1. Okay, X1 is your XPod decision variable. X2 is your blueberry decision variable. It is not $5 multiplied by 2. Do not confuse yourself. Okay, so our objective function is to maximize Z equals $7 multiplied by our number of XPods, our first decision variable, plus $5 worth of profit for all of our blueberries, which is our X2 decision variable. On on a quiz or an exam, I could literally just ask you, what is the objective function? And you would have to write out maximizing z or minimizing z, given all of the data that I provided to you. So because you're not going to be actually solving the models on your exam, you're going to have to know what all of these different terms are between the objective functions, the constraints, the decision variables, and when we go over the sensitivity analysis, you're going to have to be able to interpret what happens when changes are made to the model. Okay, but I could ask you something as simple as, what's our objective function? Okay, next are constraints. Well, we've got two constraints. Okay, we have two constraints. Our first one is the electronic time that's available. Okay, so for XPods, that is 4 hours. So it's 4 hours per XPod, and it's 3 hours per blueberry in the electronic area. We have less than or equal to 240 hours available to us. So the electronic time constraint is 4x1 plus 3x2 is less than or equal to 240. That's our constraint for the electronic time. Now let's go to the assembly time. It's 2 hours per XPod and 1 hour per blueberry is less than or equal to 100 hours available in that area, in the assembly area. So your assembly constraint is 2x1, because XPods are your x1, plus 1 multiplied by your x2 decision variable, which is blueberries, is less than or equal to 100. You also have to add your non-negativity constraints because it has to be positive. So your x1 and your x2 will both be greater than or equal to 0. It is possible that you will only build XPods or only build blueberries. It is possible, but if you do, you will only build 0 of the other product. Okay, so here is everything that we just went over. Our decision variables are x1, that's our number of XPods to produce. Our x2 is our number of blueberries to produce. Our objective function is to maximize profit. So we're going to maximize z equals $7 multiplied by our first decision variable, which is XPods, plus $5 of profit multiplied by all of the blueberries that we make, or our x2 decision variable, subject to the constraints, which are our electronic constraint is 4x1 plus 3x2 is less than or equal to 240. Our assembly time constraint is 2x1 plus 1x2 is less than or equal to 100. Both of them must be positive, so they have to be non-negative, which is our x1 and x2 greater than or equal to 0. And so our task for Glickman Electronics is to find the product mix, that combination of x1 and x2 that satisfies all of our constraints for assembly and for electronic, that yields the best value for the objective function, which is to get us our maximum profit for this organization. We want to maximize profit given our constraints, given our two decision variables of x1 and x2, and we want to find the maximum amount of profit. We don't care about the other feasible solutions. We want to maximize profit. That is our objective function. All right, and then just a summary of everything that we've gone over on these first 15 slides is how we formulate our model. Is we define in words the objectives that we're trying to achieve. We list out the decisions that are going to be made. We write out our objective function. We list the constraining factors that affect these decisions. And some key definitions that you'll need to understand are your decision variables. Those are controllable input variables that represent the decision to be made. Our objective function is that's the evaluation criteria. And then our constraints are our limitations or requirements that have to be satisfied by the solution. So the decision variables, what mix of items to produce, the objective function, what will help me maximize my profit, and our constraints, how many labor hours and machine hours do I have that are available to me. So those are your key definitions. So in some of these next couple videos, we're going to go through how we create these models using the simplex method, the algebraic method, and when we do get our answers in the answer report and the sensitivity analysis, how do we make sense of it all, and what happens if things change? How does that affect either our capacity or our profit if business circumstances change? So that's what we'll go over in the sensitivity analysis.